Welcome back to the Joys of Chemistry. I think you're going to enjoy what we're working on today, and I hope you can join in and learn something. Or you can just pull up a chair and relax. And if this is your first time watching, I'd like to extend the offer. Just pull out your own easel and paint along with us. So I thought today we'd just do something fun, you know? It's going to be you'll just have a good time. So let's get started. Today, we're going to be working on some electrochemistry. So we're going to transfer some electrons. And remember, we're always going to want to do that in a redox or reduction and oxidation format. So first, let's start off with a galvanic cell with some happy little beakers. So we're going to use our midnight black for that. So let's draw our beakers here, get some paint on our brush. Here we go. Got some more. Got to make very clear, defined lines. We'll draw a little friend here to the side, and we'll give him a nice solid base here. We'll draw on our little countertop, our lab bench, if you will. There we go. Beautiful. And so now that we have our little beakers here, you know, this is where everything's going to happen. So these are going to do really big things in the future, you know. But first, we need to draw on some liquids here. So these liquids can really be anything, but they're just going to basically be what the solutions that we're going to have later on. They're going to come into play. We're going to have a bigger role later on. So let's draw on our little water lines here. Okay. Pick up some more blue. Using our phthalo blue here. Make these more clear, defined. There we go. And it looks very liquidy, but that's kind of the effect that we're going for, just to show that these are our solutions. Let's define these a little bit more. There we go. Very nice color here. So we got to give it to both of them here, and now we're gonna darken up this one as well. We don't want him to feel left out. And so I'm gonna clean off my brush here, and you're always gonna want to make sure that whenever you're changing colors, you're cleaning off your brush in your water and drying it up. So I'm gonna actually change my water now. It's getting a little dirty, so I'll be right back in just a second. Let me change it out over here and dry my brush.
So now that we're back with our nice clean water, we're going to start drawing a little bit of rectangles here. Just going to dip our brush, going to pick up a little bit of the black. There we go. Just going to draw two nice rectangles here. Just nice little rectangles here. Inside each of the beakers. There we go. There's one. And we'll give him a friend, because everyone needs a friend. There we go. Grab a little more. There we go. Very simple shape, very simple. And what these are going to do is these are going to act as our electrodes in the following problem. But to make sure that this whole reaction works out, we're going to have to add a salt bridge here. Just drape it over the top. Drape it over top of each of the beakers. There we go. Nice. Make sure they're in the solutions or else this isn't going to work. This salt bridge, this connects everything together. It allows everything to happen. I like to think of the salt bridge as a city park where everyone can come together and share ideas, or in this case, charges here. And we're just going to transfer ions in between it. Without this little salt bridge, none of this can happen. It's amazing how the little things make everything happen, isn't it? Alright though, we need to make sure that these two things here are connected. So we're going to make a nice straight line in between them. Just make sure they're connected. Both electrodes. Nice and simple. Down one to the other. There we go. Nice and simple. And see, this is where our electrons are going to be transferring. This is where the direct transfer is actually going to happen. And that's our whole goal in electrochemistry, to transfer a little bit of electrons. And this is all going to make it happen. And to help you understand our little world, we're going to have to make sure that these electrons and solutions have some names and have some characters. We're going to make it personal. Here, let me just wash off my brush. I think we can call this one Gold. That's a good name for him. Just gonna take this, we're gonna dry this off. Make sure you always have a dry brush when you switch to another paint, because if you don't, you might accidentally mix two paints that you don't want to mix. So here we go, just drying off our brush. Gonna go in, grab a dab of water, apply it into our paint here. Nice and simple. Grab a little bit of this. There we go. We're gonna just paint him in. Dandelion yellow is the color we're going to be using for this. Just nice and simple. Look at that dark color. Nice, beautiful. Make sure we even it out. That's good. And Goldie here, he's a little bit of a taker. You know, one of those people. They kind of take everything from other people, and that's why he's going to be acting as the cathode in this. We'll get into that later. And for this guy, we'll name him Silver. But right now, as you can see, we don't have a silver color. So we're actually going to have to mix it up. We're going to have to mix some of the paints we already have. Very simple painter's technique here. So first, we're going to have to grab some Midnight Black, pop that open, and we're going to use some titanium white in here. And
what we're going to do here is we're going to take our colors, and using this, my favorite tool, we're going to mix these two colors. We're going to take our Midnight Black, grab some of that up here, put it down onto our palette, a nice clear palette. There we go. Just a little bit. This is going to be more white than black in order to get our cathedral gray. We'll give it a little bit more black than that. Here we go. Good, good. Now we're going to take our titanium white, and I'm alright with mixing these a little bit. Get up our cathedral gray made here. Swirl it around, nice circles. Okay, grab a little bit more. Alright, and now we're going to take this and apply it, and we're going to make our silver cathode using our cathedral gray. Beautiful, look at that gray. Nice, dark enough. We can even take some of the outside of this beaker, this black, to blend it in if we want it a little bit darker. I think it's perfect just the way it is. So there we go, we have our silver cathode. And now, we have 1 molar solutions in each of these. And so in our gold beaker, we're going to have gold nitrate. And in our silver beaker, we're going to have silver nitrate. But these solutions, they really can be whatever they want, as long as they have the ions of their electrode. Then really anything goes. So how I determined that gold here was the cathode is because the cathode is where reduction happens. So if we compare it to silver using our handy dandy reduction potential table, which I'll grab you down here. So if we just grab our reduction table here, pull that up, we can see that gold, or Au3+, has a reduction potential of 1.5. And then if we compare that to the silver, the Ag+, it only has a reduction potential of 0.8. So this means that because gold has the higher reduction potential, it is going to be the cathode, and silver will be the anode. So naturally, electrons are going to be transferred from the anode to the cathode, or in this case, silver to gold. And so in order to show that, I'm going to draw some electrons over here. So let me grab my palette and do that again. And in order to show this, what the heck, we'll use some alizarin crimson. So let's take that and draw some little dashes here, or negative signs, to represent the electrons moving across this to the cathode. We'll give it a little arrow to show what direction it's going. There we go, perfect. And so the problem is, with this transfer of electrons from the anode to the cathode, now we're going to have this big, sad, negative buildup over here on the cathode. And that's where our salt bridge comes in. So this salt bridge, the salt which has been soaked in a liquid, it disassociates. And so what it's going to do is it's going to give some of its happy little cations over to this cathode solution to brighten up its day. I really like to think of these cations as, well, as you would expect, cats. Little kittens that just head on over to this cathode solution, which is feeling down because of these electrons. So I'm going to draw a little positive sign here. Here we go. I'm going to draw an arrow showing which way those cations are going. But also, because this anode solution is losing its electrons, we're going to need, there's a very positive buildup over here. You know, some of those people are just a little too happy. Yeah, so the salt bridge, though, it fixes that too. So what we're going to do is this salt bridge is going to send over its negative anions to this anode solution. So let's draw that in. We'll draw our little negative sign here. Get some more alizarin crimson. Alright, and we're going to draw an arrow sign. Perfect. Now we can see that these anions are going to this. And you know, this salt bridge, it's really just amazing. It sort of acts as this equalizer for the solutions. So while all this is happening, energy is being produced because these electrons are being transferred. And this is going to be shown in the form of volts, making up the galvanic cell's voltage. This voltage can be calculated using that reduction table I showed you earlier, and I'm going to show you how to do that here in a second. But first I got to wash off my brush and dry it off over here. So let me go do that. Down here. But actually, first I need to clear up this water because it's getting pretty dirty. That alizarin crimson really muddies it up. So I'm going to go change out my water over there, and I'll be right back.
Welcome back. So now while I was gone, I had the liberty of washing my brush as well as making sure our solutions are clear. So as I said earlier, we're going to explain how we calculate the theoretical voltage for this. So we need to start off by talking about how it's classified by volts. And volts is the unit that we're going to be using in this. So if we simply take the cathode's reduction potential, which we got from that handy dandy chart I showed you earlier, and subtract the anode's reduction potential, we're going to get the theoretical overall voltage of this cell, the cell potential. So if we're trying to find this one theoretically, let me see, what color should we use here? We'll just grab, I don't know, maybe use some phthalo green. Grab a little bit there on our brush. Might be a little watery. That's okay. So we take the reduction potential of the cathode, which we said earlier was 1.5. A little bit watery. Just darken that up a bit. There we go. So 1.5 volts. Go. So that's our cathode. And then we will subtract the reduction potential of the anode. So subtract. And we said that this one was 0.8 volts. And using some simple math, we will know that this will come out to equal 0.70 volts. And that's going to be our overall voltage that we have, theoretically, if everything goes to plan. And since this is positive, this reaction is called what is known as spontaneous. Basically, it just happens. It's natural. Kind of like this painting. We just took our imagination and put it on the page, just naturally. When this is the case, we refer to this as a galvanic, or even a voltaic cell. They mean the same thing. The reaction is what is called thermodynamically favored. However, if we tried to make the electrons go from the gold to the silver, then this wouldn't happen naturally. We would need to apply some energy into the system to make those electrons go the reverse way. This would be called an electrolytic cell, which has a power source, as I said. We'll make another video for that later, but this one is purely about galvanic cells. And going off of that, we'll have to address some of the common mistakes that newer painters experience when they're trying to work and draw these galvanic cells. One clear indication that it is a galvanic cell is that it has no power source. As I said earlier, if you see a power source, then you know it's an electrolytic cell. Don't get confused though, because sometimes they will put something that looks like a power source up here, but in reality that's just the voltmeter. That's the thing that's reading the amount of volts that we're getting here. Also, make sure that you're calculating the voltage right. The solutions are 1 molar solutions of our respective solution. So for this one, we have gold nitrate and silver nitrate, and those have to be 1 molar. Otherwise, you have to use some complicated equation that no one wants to learn anyway by some nerd guy. Another thing is when you're looking for your reduction potential, make sure that you don't get the two mixed up. Make sure you remember that the cathode is the higher of the two, and the anode is the one that is beneath that. Make sure that you find the right voltage and don't subtract them the other way either. Also, make sure that you have a negative sign here always, and even if this happens to be negative, make sure that you distribute that negative in and make it positive. Don't try to fool around with the equation, make one negative and one positive. That's not going to turn out well for you. So to make sure and recap, we're going to make sure that we have a clean color in on our brush. Just nice color. I'm going to dry it off here.
So I'd like to just do a quick summary of what we've gone over today. So we're working with a galvanic or a voltaic cell here. So we drew in our beakers and our tabletop with our midnight black color. And then we moved on with our phthalo blue to draw in these liquid solutions here. And then we drew in our electrodes once again with that midnight black, and we also added in our salt bridge and our wire here that was going to transfer the electrons. And then we colored in and gave a bit of a personality to our electrodes. So we had here for our gold, we had a dandelion yellow to make it that gold electrode, or our cathode later on. And for this silver anode, we used a cathedral gray, which we mixed from titanium white and the midnight black over on our clear palette. And so then I decided to more give a visual for these electrons transferring. So I used our alizarin crimson to show this transfer here with these negative signs going over. And I showed how the salt bridge acts as that equalizer to give the cations and the anions to their respective solutions. And then I even went on to explain, using our phthalo green here, how you calculate the voltage, using by taking the reduction potential of the anode and subtracting that from the reduction potential of the cathode to get our total cell potential in volts. So I'm so glad that you guys could all join us here today on this episode of Joys of Chemistry. I hope you learned a lot, and hope you can join us next time. See ya.